Okay, so we will continue with the application of integration, and this time we will determine the area between the two curves. So determination of the area could be a process in which you find the area of the outer function minus the area of the inner function. Or it could be what, as I have discussed with you last meeting, wherein you're going to use the summative area of the differential element chosen. So what do I mean by the summative area? So allow me to annotate here. If this is your differential area, so then you have the differential dx for the width of this rectangle, and for its length, you have the y. So as discussed as well, if this is your, we label this as curve number 1, and this one, the brown one, as curve number 2, the y that you have written there will be, so as you can see here, y of x sub 1. So meaning this is the y of curve number 1 minus the y of curve number 2, representing the length of this differential element. We multiply it to its width, which is dx. Then we're going to check the boundary for these two, for the area enclosed by these two curves, and that would be from A. So you have A here, so it's your lower limit here, and B is the upper limit. So you need the x coordinates of these points here, A and B, and you place it as the limits of your integration. That is if you use the differential element, which is vertical. So you take the summative, the summative area of the differential elements, the vertical differential elements on this area enclosed by these two curves. Now you can also use the horizontal elements. In this case, you have dy. So if in here you chose the uppermost point minus the lowermost point as the length of your differential element, in here you will choose the farthest point to the right minus the farthest point to the left. Okay, so in this case, you will have, if this is your curve 1, again, and this is your curve 2, so then you will have the x of curve 1 minus the x of curve 2, this time as the width of this differential area. Its length will be dy. So as to the limits of your integration, so you see that these are your points of intersection for the two curves. So as for your limits of integration, you're going to use the y coordinates of these points. As you can see, you use c for the lower limit, and you see d as the upper limit. So you use the y coordinates of these 2 points of intersection. So question, however, how do you determine these points of intersection? We're simply going to solve these 2 curves simultaneously, meaning you are to equate the equations, or just like what you have learned in algebra, substitute the y of one curve as y of the other. Then correspondingly solve for the x. Once you have the x values already, you substitute it on any of the equations of the 2 curves and solve for the y. The values of the x and y that you will be getting out of those, out of that particular procedure will be the coordinates of these 2 points of intersection that you have. So the principle that you're applying here is exactly the same as if you are determining the area enclosed by a curve and a line, or a curve and a particular axis. So that would be the same as this one. You still determine the summative amount of the differential areas that you have chosen based on the limit of integration, or based on the boundary of such area. Okay, so that's generally how you do it. And I think you have learned that as well last Tuesday. Okay, I will clear my markings. Then we proceed to the next slide. Ria Noble, okay. Admitting them now. Thank you. So we now proceed to the next slide. Now, in the case of this particular region bounded by these two curves, so if you have chosen the differential element to be this purplish area, this one, so you'll have again dx here, and this is your y. So when you write the integral representing the area of that particular region, that would be, so you have this upper point and this lowermost point. So you will have f of x minus g of x. You will have here dx. As to what would be the limits of integration here, that would be the points. That would be the points of intersection of these two curves using their x coordinates, that is. So I will just place here x of 1 to x of 2. So generally, that's how we do it. So I have here my markings. And we proceed. So the red shaded area, so you will have that one. Or simply put, that's the equation that I have written a while ago. A and B are the x coordinates. So this one, the x coordinates, sorry. So the x coordinates of this particular region. So the chosen area is just this, bounded by these points A and B. So you're going to use the x coordinates of points A and B. Just interrupt if you have any questions. Now, if you have this, you can use the, what we call the vertical element. But however, if you've noticed, your area is below the x-axis. And as such, the areas that you will be getting are negative. So what you're going to do, you simply write the negative of such area. So the same formula applies for this scenario. In here, you have f of x and g of x. For these two curves, you have A and B here. So that is the area is equal to the function of x. This is your function of x, the uppermost curve here. So if I will annotate, so this is your differential element, it's dx. So your uppermost point is f of x, the lowermost point is g of x. The area that you will be getting is of course negative. You just have to write the positive of that because it's below the x-axis. So your limits will be from A to B. Oh, sorry. So So your limits here will be from A to B because here, this shaded area is bounded by these values of x from A to B. So you will have the limits from A to B. So it's function of x minus g of x. I think that's true for this also, function of x minus g of x. If you will choose this differential element, so this is dx, and you have here the function of x, and you have here the g of x. So if you continue reading on what's in this slide, note that the function of x comes first, as the function of x is a higher function. So we choose the higher point in our differential element and subtract the lower point. So that is the function of x is greater than g of x for all the points in the required domain. So when you speak of domain, that is all the points here included in the shaded area. What if you have these two curves? So, but what if the two curves cross over? So you see this? You have this particular region, and this particular region. And you are asked to determine the sum of the areas of these three regions. Or you are to determine the area bounded by these curves on the boundary, or from the interval rather, A to B. So meaning you are to determine the area bounded by g of x, this one, and f of x on the boundary from A to B, or bounded by A to B. So that would mean that you are to determine this area, okay? This area, number 2, and this area, number 3. Again, in principle, we will do the same thing. We will add up all the areas that are enclosed by these curves in the designated interval or domain. So in the domain x greater than A, or x greater or equal to A, but less than B, so less than B meaning it's all in this region, the curves cross over twice. So they cross over twice. This is the first crossing. This is the second crossing. Therefore, 3 separate areas are to be calculated. Noting that your g of x is this one, is greater or equal to the function of x. So this is your function of x, and this is your g of x in regions 1 and 3. So in regions 1 and 3, it is your g of x that is higher than your function of x here. However, in region 2, that's the other way around. G of x is higher. You may not see my pen. So in sections 1 and 3, or that's region 1 and 3, your g of x, this is your g of x, is higher than function of x. So it should be g of x minus f of x. In section 2, you will have to do it the other way around. That should be g of x minus f of x. No, f of x rather minus g of x. In here, it's g of x minus f of x. You just have to be careful in assigning the function to be subtracted from what, because the higher function should always be written first, subtracted by the lower function. So this is it. So in area 1, wherein you have this coordinates A to C1 for their x coordinates, it should be g of x minus f of x. In area 2, it's the other way around. F of x minus g of x. Your boundary will be C sub 1 and C sub 2, or C sub 1 to C sub 2. For this area 3, you will have again g of x over f of x. So you have g of x there. This one over f of x. And it's bounded this time from C sub 2 to B, or by points C sub 2 and x to point B. Okay? So let's have this 8th example. Find the area bounded by the functions 4 over x, y equal to x, and the verticals, or the vertical line, x equal to 1 and x equal to 3. So let's look at that particular area. Of course, step 1, you have to draw a very good diagram, because you can't get a good understanding of what particular integral expression you will write if you haven't drawn the said area. So you have to draw the line, or you have to draw this curve, xy equal to 4. If you do cross multiplication here, you have to draw the line y equal to x, and you have to draw these 2 vertical lines. And that would be this particular illustration. Okay, give me a moment. I will just increase the size of this so you will see. So you get to see a bigger illustration. Okay, so we'll project it again. So you have to draw a good curve, and that curve will be this. Now, if I will annotate, this is your line y equal to x. So this is your line y equal to x. The 2 curves that you're seeing here are actually this xy equal to 4 curve. xy equal to 4. If you do cross multiplication, you will have xy here equated to 4. And that would be these curves here. Now, the lines 1, x equal to 1, and x equal to 3 will be the lines here, vertical lines. So, we'll have another projection of this here. So, you will see now the exact area. So, note that x equal to 1 to x equal to 3 is the required domain. So, let's see where those two lines is. You are to determine the shaded region. And this is now the area that we are to determine. This is your y equal to x line. This is your function of x equal to 4 over x or y. So function of x class here is the y. The g of x here is the y. So meaning it's a function of x. F is a function of x. G is a function of x because the right side here are all in terms of the x variable. So this is your line, y equal to x. This is your curve, y equal to 4x. And this is the vertical lines, x equal to 1 and x equal to 3. If you look closely, the area that we're trying to find is this area here. These two areas here. And I think you fully know how to do it. So you will not know how to write, or it would be difficult for you to write the integral that will solve for the area of these two regions if you haven't, in the first place, drawn properly the curve, the line, and these two verticals, or these two vertical line 1 and 3. Now, the line y equal to x is so easy to plot because whatever is the value of x, that would be the y. You just place points there and then you connect. It will pass through the origin because this line doesn't have a y-intercept. The curve, however, you have to assign values. So if x is positive, your curve will be here. If your x is negative, your curve will be below the y-axis. So that is why it's in this side. Because if you divide by a negative value here, it will be in here. So that is why you have two curves, one on the first quadrant and one on the third quadrant. So this is the shaded region in which you are to determine the area of. So set up the integral for step 3. So we'll just clear the markings here. So this will be your integral for this one from 1 to 2. So you're going to look for the integral bound or that has the limit 1 to 2. If you choose a vertical element, so you will have function of x over minus g of x. So that would be 4 over x minus x. So that's the reason why you have here 4 over x minus x from 1 to 2. And you have x minus 4 over x from region 2 to 3. Or bounded by the coordinates of x 2 to 3. So it's the other way around. Wait, class. So it's the other way around with this integral. In here, if the limits is 1 to 2, it would be function of x minus g of x. If the limit is 2 to 3, that would be g of x, this line, y equal to x, and this curve, which is 4 over x. So, negative na siya sa original mong expression. And you're using a different limit. And that's what is happening here. So you set up the integral, you evaluate the terms in your integral or evaluate the integral, you substitute the limits, and the rest would be just a matter of doing your algebra or arithmetic in this case. Because you don't work on x here anymore, but rather you work on real values. So this is the area or the sum of the area of the two regions. One bounded from 1 to 2 by the coordinates 1 to 2, and then second 1, 2 to 3. Okay? Example 9 would be this. So, you have this pink region. You are only interested in finding the area bounded by these two verticals, x equal to 1 and x equal to 2. So that would also be your limits of integration. If you use a vertical, if you use a differential element which is vertical, and this is your dx, then you will have to have your function of x, which is negative x squared plus 4x plus 3, and your g of x, this one is negative x cubed plus 7x squared minus 10x in here. So if you do your maths, that would be this portion, f of x minus g of x. You can see that f of x minus g of x. Actually, you can have it in just one expression. This is your f of x. And the equation is this one. And this is your g of x. The equation is this. And you just do the mathematics afterwards. Okay? So it's like when you determine this area bounded by these two curves enclosed by these two verticals, it's like finding this entire area and subtracting this small area. This small area here. You subtracted it from the entire area. So it's like finding this one. But it is more straightforward if you simply write the differential element right on the shaded area. That way you don't have to do this. Okay? So if you substitute, you just substitute. You copy your function of x expression, subtract the g of x expression, and do the mathematics. Most of these are just power rule. The only mistake that you are most likely to commit here is just if you are in a hurry, which most of us are guilty of, then the simple substitution of the values of the variables here will not get it because we are in a hurry. So in this case, the area has a value of 49 over 12. Okay? Okay, example 10. This is our example 10. The area, find the area between the function negative x squared plus 4x and g of x equal to x squared minus 6x plus 5 over the interval 0 to 1. So this is the interval 0 to 1. This is 0 and this is 1. So you are to find the area in the pink shaded region here. So you have two areas. You have this one. Have this differential element here. Let's say this is your area 1 and this is your area 2, which can also use the vertical differential area. Okay, area 1 and area 2. So, but before you can do determination of this area, you need to find the very important, wait, I use a different color. You need to find this very important point of intersection because that should be the limits that should be reflected in your integrals. You need to know the coordinates here. Okay, what are the coordinates? So when I discuss finding the intersection of curves or lines, you simply have to equate the y of one with the y of the other rather. So if this is y equal to negative x squared plus 4x, and this is y equal to x squared minus 6x plus 5, in their points of intersection, these two y has to be equal. Same thing with the x, the equivalent x for these two y. So you're just simply going to equate the two. And that's what you did here. You determine the corresponding value of the x. And in that sense, you are getting two values here for the x. You have 1, which is 5 plus the square root of 15 divided by 2. And the other one, which is 5 minus the square root of 15 over 2. So since you have two values and you are interested only in this particular point of intersection here, you have to choose the x value, which is positive. So if you have 5, minus the square root of 15, your answer is 1.12. And if you're going to divide it by 2, your answer will be 0.56. So 0.56. One answer is 0.56. That is if you do subtraction. If you do addition, you have 5 plus the square root of 15. And if you're going to divide it by 2, your answer is, take note, the other answer is x equal to 4.436. Now this time, you need to really validate which of the two x's do you think is appropriate for the x coordinate of this point in question. Which do you think is acceptable? You can write your answer on the chat box. Which of the x values that you got for this point is acceptable? Okay, the answer, 0.56, the first one. This one, I'll just change the color. This one is not acceptable because in the first place, it's beyond the bounded region 0 to 1. You're only interested in this region, but 4.46 is beyond 1 already. So meaning you will not use this. You will use the 0.56. So when you write your integrals later on, the first integral will be from 0 to 0.56. The second integral will be 0.56 to 1 in terms of the limit of integration in which you have chosen the differential element to be vertical. Okay? So if I will clear my markings and we go to the next slide, it would be something like this. So you will have 0 to a, and that a will be the 0.56 that we have solved a while ago. And you'll have a to 1. So you have this one. You have here 0 to a and a to 1. You just do your integral here and then substitute the limits. So this is your final answer for the area that you are determining. So in here you get to see how do you determine the points of intersection or point of intersection between curves in this case. So it could also be a curve and a line or a curve and any of the axes. Any questions? Okay, so we go to the 11th example. Determine the area of the region bounded by y equal to 2x squared plus 10. And that would be this red curve here. And y equal to 4x plus 16. This y equal to 4x plus 16 is a linear equation. So meaning it's an equation of a line. And that line is this blue line here. This curve, which is a second degree equation, is this red curve here. Now, it is bounded by these two vertical lines, x equal to -2. So as such, you start here with x equal to -2, and you're going to end with x equal to 5. In this sense, you will be determining 3 areas. 1, 2, 3. If you're going to choose a vertical element, something like this here, something like this here, and something like this here, you won't have any problem at all because the differential element or the differential area that you have chosen for each of the sections here, in which you are to later on take the sum of the area of, are uniform in whichever section you would be. It will require the same representation of the area of this differential area, which is that of a rectangle. The same lang. So, okay lang siya. You cannot use the horizontal. In here, by the way, you cannot use the horizontal because at this part here, you will have this line and this line, but at the bottom part, you will have this line and this line. So it will not be uniform anymore in terms of the representation of the differential area. So when you choose the differential area, it has to be uniform for the section in which you intend to find the area of. So you have here 3. From -2 to -1. So this one, you have the equation of the curve, 2x squared plus 10. You have to subtract the equation of the line, 4x plus 16. The second area is this. This time you have to start with the line minus the equation of the curve. And for the last area, it would be the curve, 2x squared, the curve 2x squared plus 10. And for this line, you subtract it from the equation of the curve. This line is negative 4x minus 16. So simplifying, it would be this. Look at the limits of integration. You have 3 to 5. So question, how did you find, again, these points of intersection? So notice, let me check, Lasha. Let me just clear my markings. Let me just first make this bigger so you will see. This is bigger now. So you have -1 and -2 to -1. You can see it in here. You have that. Then you have -1 to 3. You have this. And 3 to 5. This one. So the x coordinates the boundaries of the 3 areas in question. If this is not given, or if it's not shown properly on the graph, or even more so, class, which makes it more difficult, what makes this more difficult is if the curve and the line is not plotted. This one is easy because you already plot, the curve is already drawn, the same thing with the line. But if you're the one who is drawing the curve and the line, that would be an added challenge. But to make things, so as not to, let's say, stress you on the plotting, it's very easy. Just substitute, just select a value of x. Place here a value of x, solve for the y. That's 1 point. Place here a value of x, solve for the y, another point, and then draw the curve. So the more points that you have, the more accurate is your curve. Same thing with this line. Substitute an x, solve for the y, that would be 1 point, and then another one. You connect it, that would be this line. Once you have the curve and the line, it would be easy to see how or what would be the areas that you're going to determine. In that case, that would be this 3. Again, if the intersections are not given, you have to, in this case, class, you have to find the point of intersection. Is this particular point of intersection and this particular point of intersection. How? As I have discussed with you a while ago, this y of the curve will be equal to the y of this line at their points of intersection. So meaning you will just have to equate the 2 equations. Okay? Y of the curve, which is 2x squared plus 10, should be equal to the y of the line, 4x plus 16, at the point of intersection. So you solve for the x here. So you will be getting 2x's, true, because you have 2 points of intersection here. Okay? You need not, in this case, solve for y. If you're asking, how do we solve for y, means you just choose any of this equation to substitute the values of x that you got from here. Substitute it either on this equation of the line or this equation of the curve. Anyhow, the x that you'll be getting, as you substitute to these 2 equations, should be equal because they are referring to the x of the point of intersection of the curve and the line, and they are said to be the same for the 2. So any equation would do if you want to solve for y. But in this case, you don't need it because you only need the x. Why? Because you are choosing the vertical, the area. So it should be a dx, differential area. So dx. So you need only the x boundaries. Okay? I'm sure you know how to do the maths here for this one because most of that is just power rule. Then after that, substitution. Okay, any questions? Any questions, class? Okay, then, okay, wait. Okay, we go to the last example on this before we go to solids of revolution. So determine the area of the region enclosed by. So this time, your curves are in terms of trigonometric function. So I have chosen this that way you will not only limit your curve tracing to algebraic expression. If you intend to solve for the value of y given the x, and you want to use radian values here for the x, for example, you want to substitute here, you want to substitute here pi, or you want to substitute here pi over 2. These are radian values, or you need to substitute here 10, 20. Just make sure for the x, both for the x here. By the way, cosine of x na siya. Make sure that you change the mode of your calculators to radian mode. Change the mode of your calculator to radian mode because you cannot get an answer correctly if you substitute values in radian to x and get a corresponding radian value for y. So change the mode of your calculator to radian mode. Then once you have the corresponding value of y for x, then you just plot your curves. So the curves that we have in here, you could see this is your curve. Y is equal to cosine of x. And this is your curve y equal to sine of x. So you are to determine the area bounded by these two curves on the region x equal to 0 to pi over 2. So notice that the values here are not in degrees but radian values. So that's the reason why you need to change the mode of your calculators to radian. If that is the case, you need to get this very important point of intersection. So what is this point of intersection here? You will be able to do that by equating these two, sine of x, cosine of x, since they are the same. So sine of x is equal to cosine of x. Sine of x over cosine of x is equal to 1. What is sine over cosine? I'll just place here, tangent of x is equal to 1. What angle will give you a tangent which is equal to 1? That's the 45-degree angle equivalent to pi over 4. So if you check in your calculators now, tangent of 45 degrees, if your mode of calculator is in degrees, is 1. The tangent of pi over 4, if the mode of your calculator is in radian, is also 1. So that's the reason why you get to see that this point of intersection between these two curves has an x value of pi over 4 in radian or 45 degrees in degrees. So when you write your integration, notice that for this area, the first area, you have the limit 0. You have 0 to pi over 4. For the second area, you have pi over 4. Start here. This is the second area, 2 pi over 2. Okay? Now, you choose, of course, you choose the vertical element. That's very obvious because that would be enough to determine uniformly the two areas because this differential area will be true for all sections here. So for this one, it would be cosine of x minus sine x, upper point minus lower point. For this one, it's the other way around. So you have g of the sine of x for the blue curve minus the cosine of x in the red curve. Then evaluate your integrals. Then substitute the limits. So you get to see that this is the area Actually, the sum of the areas of the green shaded region. Okay? That's how we determine the area. And that's how very important is number one, curve tracing and plotting of lines. Because if the figure is not given, it's really difficult for you to determine the area that is to be determined. Second, once plotted, it's very important that you solve correctly the point or points of intersection. I'm sure you know how to find the area using integral calculus for the shaded regions or for the region in question. Okay? Any questions before I close the markings? None? Okay. We'll close this one. And I think this would be the last on plane areas. Okay? After this, we'll have solids of revolution. That way, when we meet each other next week, ang continuation naman lang sa solids of revolution, ang akon i-discuss, of course, after the quiz. Okay? We'll check first our schedule and we'll update you on that. Now, any question here? So if there's no question, I'll stop sharing for now.